Good morning, everybody. Can you all hear me?
Yes.
You can hear me? Okay, great. All right. I hope you all had a good weekend. So a couple of things. Again, I'm going to keep reminding you, Friday is your first exam. You're going to come to room S102 and begin the exam by 2 o'clock. Again, make sure that you clear yourselves to come into the classroom, which means you have to use the app on your smartphone before you come in, just to get cleared. You got to show me that you're cleared. Let me see if I can find mine. Just a second. My phone's very slow. Okay, maybe I won't show it to you. Anyway, my phone's taking a long time, but I was going to show you folks on the app. There's a window that'll show up saying that you're cleared, and I need to see that. Okay? Hopefully your phone is not as slow as mine. It'll show up somewhere in this window, in a window on your Sierra College app. I don't know what mine's causing problems. So I need to see that. You also have to wear a mask as you take the exam. You only need a scientific calculator. If you don't have a scientific calculator, I can provide one for you. Our group only has 11 students, so you'll have a lot of room to spread out. Okay, you'll have plenty of room to spread out to take the exam. Those of you who are waiting for me to regarding the SPS questions, I'm still waiting to hear from them, and I will respond to you hopefully later today. I did email you practice exam for the in-person version. Please take a look at it. I wrote it very quickly because I've just been busy. Take a look at it. Try to go over it. You should even try doing the online version too. The other one that's on Canvas. The more problems you do, the better. The only way you're going to learn this stuff is to practice. Okay. There's a key to the practice exam I sent you guys yesterday. Okay. In fact, I sent you two. One had a mistake on it because I was using an old exam. Use the latest version that I sent you. Okay. Any questions regarding the practice test? That practice test is a little bit longer than the actual test. I actually think that the actual test might be a little short. I'm going to give you an hour and 25 minutes to take the test. But I'm thinking it'll be a little bit shorter. I mean, you'll be able to get done earlier than that. Of course, that's me saying that. So hopefully you will get done quickly. Okay. Questions regarding the test?
It's no notes, right? It's just...
No notes. So the first page, if you look at the first page of the practice test, that's the notes I give you. It has all the equations you need. Okay? So that first page is your crib sheet. You'll get the exact same one. Unless I forgot an equation, then I'll add it in. But I'm pretty sure I got all the equations in. And so you just need to know how to apply them. Okay?
Okay.
Other questions? Or concerns? Thursday, I have, the day before the exam, I have office hours from 5 until 6:30. Okay, so please come then if you have any questions. All right, I'm hoping you're come close to finishing up the first homework assignment. A couple more reminders. Read chapter 23. We're going to start our next unit today. Like I said, the web assigned the first one is due Wednesday. And then your first lab where you have to build the apparatus is due on Monday. Okay, so you have several things you got to do. I wanted to bring up something that might have caused a little bit of confusion in the last lecture. It had to do with me working on a problem where we had these two objects of mass m. They collided into each other and stuck together. And I did the problem. It was a completely inelastic collision. They had the same mass, and they're going at equal but opposite speeds. And I did the problem in our frame, the lab frame, so that'd be like, meaning like this person standing here watching the two events. Then I did it from the event, from the frame of a person standing on the object going to the right. So I drew the picture again. Okay. And I drew a coordinate system that moves with this particle, and I drew a coordinate system that moves with this particle. This particle moves to the left, this one moves to the right. And I said, suppose someone who's in this coordinate system, or someone standing on that particle, is observing the process. How do we write the velocity of itself and the velocity of the other object? Well, if you're sitting on the particle, that you're moving with the particle, and so that velocity of that particle is 0. But what about the object coming towards you relative to you? Well, first of all, the Earth's reference frame is moving to the left. That observer according to you is moving to the left. Okay, I'm sorry. That observer who's on the particle sees A moving to the left because U is moving to the right. And of course, this particle sees this object coming towards it with velocity minus U. So if this person considers itself as the stationary frame and that the moving frame, then you need to use this equation to calculate how fast this object is going relative to this person. So I say u sub x prime is minus u. V is minus u because the Earth's reference frame is moving to the left at u. And so I put u squared here because minus u times minus u is plus u. And I get the equation that I described in the class the other day. And of course, if u is much, much less than c, we would get the classic version of minus 2. In other words, if I'm going that way at 30 miles per hour and a car is moving the opposite direction at 30 miles per hour, if I'm sitting in the car observing this, I'm going to measure that the other car is coming at me at 60 miles per hour. Okay? Similar idea, except that, if you take into account relativity, you have this denominator term. Okay? So I just wanted to kind of clarify that.
Wait, Professor.
Yes?
Why is velocity negative u and not u?
For this object?
Yeah, so so v is in regards to the second object?
Yeah, so what we're calculating is the velocity of this object relative to a person sitting on this particle.
Mm-hmm.
And isn't it true that this particle is moving to the left?
Yeah.
And isn't it true that the Earth's reference frame is moving to the left according to this person?
Yeah.
Okay, so both velocities are negative.
Oh, yeah.
Okay.
Okay, so it's the velocity of person A is what v is.
Yes, that's right.
According to person B. Okay, that makes sense.
Yes. Okay, so sometimes it's a little confusing. When you change the reference frame, you got to be really careful. Okay, and then of course you got to do, if you're viewing the collision, the process from this person's point of view, everything will end up being positive. From this person's point of view, the velocity of this object is the positive version of this expression, and the velocity of this object is 0.
Yeah.
Okay. But then if you apply conservation of energy and momentum, you will get the same answer as we did the other day. So I just wanted to make a couple comments regarding the problems we did the other day. And it's really in the video that I have on Canvas. So I hope you watched it. You got to watch these videos, okay? The videos I put on Canvas, you got to watch them. Especially this last one. So if we're doing problems involving conservation of energy and momentum, let's just say two particles in general. Let's say U1 is bigger than U2, so it catches up and slams into it, okay? And then afterwards, let's say they stick together, just to make the problem easier. So this is the composite particle. Like they collide and stick together. What happens? Well, we got to consider the energy of the first particle plus the energy of the second particle equals the total energy of that composite particle. And there's two ways to write this energy. Well, first of all, I can do it the following way. These are initials. I'll just put 1 and 2, sorry. This is the total energy of the first particle, the total energy of the second particle. And then I'll just write big N. So I can write the total energy this way, or I can use the other equation for total energy. Although this might be a pain. In a lot of cases, if it's fully written out this way, this is going to be a pain to work with because you have a lot of square roots there. Okay, so, but that is another way to help you solve the problem. Now, in a lot of these problems, some of these terms will be 0. For example, if you have a photon, if one of these particles is a photon, then you actually, if one of these particles is a photon, you can't write it this way. You have to write it this way. But if one of these particles is a photon, then m is 0. Okay? You can't use this for a photon because the mass of the photon is 0. For a photon, E is P times C. So you have to use this form. Okay? The other equation is conservation of momentum. So I have this equation, and I have this equation. And again, when I have a photon, P can only be written as, the momentum can only be written as E over C, whatever the energy of the photon is divided by C. Okay, this assuming you're not dealing with the photon. Okay, so if either one of these is a photon, then oops, I have it backwards. Can you see the board okay?
Yeah.
Okay. So you have this equation and this equation you have to satisfy in these collision problems. However, there are some problems where using this equation and this equation is not going to be useful. If you have a photon, you can't use this for the photon. Okay, the photon can only be written Z over C. Okay, so it all depends, how you use the equations is just going to depend on what you're given. So you actually have multiple ways to solve the problem, and by you practicing, you will find the best way to approach the problem. Okay? On the equation sheet, I didn't put down the conservation of energy equation because there's so many different versions of the problem. You should know that I end up with what I started with. You don't need that equation, okay? You just need to know what the equation for E is. And you need to know what the equation for P is. Does that make sense? So in the video, I did the problem two different ways. You have a problem on the practice test where you conserve energy and momentum. You have a problem on the online test where you do the same thing. And then you have a problem in the video where I go over. So you have a lot of examples. And then you have two homework problems. Okay, so I'm assuming you're going to be good at this when you take the exam. Okay? All right. I want to do one more example on this topic. And the example is, I think, pretty straightforward. I have two protons. Actually, a proton and an antiproton, sorry. They're essentially at rest. We'll assume they're at rest, but they're essentially at rest. Their kinetic energy, I can say that their kinetic energy is way less than their rest energy, okay? And they annihilate and they produce two photons. And unfortunately, in physics, we use the Greek letter gamma to represent photons when you write a reaction like that. This is a reaction. So this is the antiproton. That's the proton. And these are photons. And these are going to be energetic photons because we're going to have a lot of mass being converted into energy. What must the energy of these particles be? Okay. I got to conserve energy and momentum. Well, if these are at rest, then all I have is the rest energy of these two particles. Antiproton and the proton have the same mass. So the total energy I just have is the mass of the proton times c squared plus the mass of the antiproton times c squared. Here, gamma is 1 for each of these two particles because they're at rest. So I just have the rest energy. Okay, P is 0. And that's going to be the energy of the two particles. Okay, I'll just write them as E1 as E2. There's actually a formal way to write it, but I don't want to write it down. Then we consider momentum. What's the total initial momentum of the system?
Isn't it zero because they're at
0,
rest?
yeah. So I have 0 equals P1 minus P2. So P1 equals P2. But for a photon, you know, this equation this is 0 for a photon. So the energy is P times C. And so what this says is E1 over C equals E2 over C. So they're the same. And so I'm left with 2 times the mass of the proton is 2E1. So E1 equals E2 equals m sub p c squared. So basically the energy of each photon is equivalent to the rest energy of each proton. I forgot what the value is. I'll just write it as 938 MeV. I think it's 938.3, I forget. And really that's it. So that's another example of an energy problem. Okay. You'll find as you do these problems, because there's a specific algorithm to solve these problems of a specific method, they tend to be a little bit easier to do than the kinematic problems. And you'll find that in physics, you spend more time doing these problems. Okay, especially if you're doing high energy physics. You spend more time doing these kind of problems than the kinematic problems. Okay, so we're done. We're done with Unit 1. Okay, we're done with all the material in Unit 1, Chapter 39. Most likely, you'll probably never see this material again, unless you're a physics major. Engineers don't see this material, okay, unless they're doing something very specialized. Let me switch the PowerPoint notes to my to the next unit. Just give me 1 second. Okay, so we're going to be looking at our second unit. The second unit covers electrostatics. So the second unit encompasses 3 chapters. From now on, every unit is 3 chapters. Okay, the notes I have are the order I used to teach the class, where I would do relativity last, but then there was nothing left for relativity. Now there's very little time left for doing chapter 34, which is really not a chapter. It doesn't have much interesting physics, at least in terms of the way we can approach the topic. Okay. So the first chapter in this unit is not too bad, but the next 2 are a little bit more difficult, because this is going to be, 24 and 25 are going to require your knowledge of calculus. Okay, it's going to require extensive use of calculus. So just be aware of that. So you want to brush up on your calculus, especially integral calculus. Okay, so if you've had, actually, what I should say is, if you've had Physics 205 here, and I know if you had it with last semester, you probably did a lot of stuff on gravity, on how to calculate fields. We're going to use the same mathematical techniques in this unit. We're going to use it extensively. So just, if you want to review something, you want it from Physics 205, you want to review the material on how to calculate gravitational fields. Okay? All right. So I need to go through some of the slides here, because we did some of this in lab. Hold on a second. Let me skip a few. We've talked about properties of charge. We did it in lab on Friday. We know that like charges repel, unlike charges attract. Okay. And charges of scale are like mass. The only difference is mass can only be positive, charges can be positive or negative. Okay. And that's what makes the difference between the electric force and the gravitational force, because the gravitational force is always attractive, even though the two masses always have the same sign. Whereas here, in order for you to get an attraction, the two objects have to have, or the two charges have to have opposite signs. And we know that charge is discrete. In fact, mass is discrete too, because any mass depends on the mass of the proton, the mass of the neutron, and the mass of the electron. Whatever object you have, the total mass is a linear combination of those particles, pretty much. Okay. Unless we start taking into account relativistic effects. Now, Coulomb determined an expression for the force between two charges. And we're going to use letter Q again, like we said the other day, to denote the force between the two. We're going to use letter Q to denote the charges. Okay. Coulomb determined that the magnitude of the force is written in the following way. Some constant times the magnitude of the first charge times the magnitude of the second charge over the distance between them squared. This is called Coulomb's law. And this represents the magnitude of the magnitude of the force between the two charges. And I should be more careful. This R12 that I wrote in fact is the magnitude of this vector that goes from 1 to 2. So I should write it like this. And if I write down 1, 2 here, F12 is going to say is the magnitude of the force on 1 due to the second charge. Okay? When I write this subscript, this is the force on 1 due to 2. And R12 is the vector that goes from charge 1 towards charge 2. And we need the magnitude here. So this is just magnitude. It really says nothing about the direction of the force the way I have written it so far. There's another way to write it, and I'll show you. But I like writing it this way. Now, K is a constant. K is called Coulomb's constant.
Professor?
Yes.
Will any of this be on the test on Friday?
No, this is the second unit. The Friday's
Okay,
test.
so all is just unit 1. Okay.
Yeah, the Friday's test is just unit 1. This is all in unit 2. Yeah, so none of this is on. Well, you're not going to see anything on Friday. You're not going to see any of this on Friday's test. Okay, this is a completely new unit.
All right.
So this is Coulomb's constant. It's analogous to the gravitational constant. And the units are Newton, Coulomb squared per meter squared. If you remember, G was what? 6.67 times 10 to the minus 11 Newton kilogram squared per. Oops, I have it backwards.
Is Coulombs a capital C or a lowercase c?
It's a capital C.
Okay.
Okay. Yeah, good question. And sometimes I'm sloppy when I run on the board, but it's a capital C. So it's Newton, so for G, it was Newton meter per squared per kilogram squared. And for Coulomb's constant, it's Newton meter squared per Coulomb squared. Okay, these are the units for those constants. What do you notice about the difference between those two constants?
One's weight and one's time.
Say that again?
Or one's charge. One's charge and one is weight.
Yeah, I mean, one's related to weight, one's related to charge. That's true. But what about the size of those values?
One is massive and one's small.
Yeah, there's a big difference in those two. I mean, one's really huge, and the other one is relatively small. Okay, and that's and what that means is that the electric force is way stronger than the gravitational force. So when we talk about gravitational force, we're dealing with very massive objects like planets. When we talk about electric forces, we usually use them to describe the motion of charged particles like electrons and protons. If you're describing the atom and all the forces acting on the charges in the atom, we ignore gravity because the gravitational force is way less than the electric force. We wouldn't be able to measure any gravitational effects. At least based on our current knowledge, we cannot really determine or measure any gravitational effects. Okay. Questions on this expression? Again, it's a magnitude. I also want to say one more thing, that Coulomb's law is really valid for stationary point particles. Or cases where the objects have a behavior like point particles. What does that mean? Well, it means that the dimensions of the particle are much less than their separation. So if I have two spheres, sphere 1 and sphere 2, and if D is much, much greater than R1 or R2, then they look like point particles. If you're real far away from a sphere or any object that's charged, it just looks like a point particle, and you can apply Coulomb's law. It would be a good approximation to calculating the force between those two objects. Okay. Also, if the objects have a lot of symmetry, like a sphere, you can treat them like a point particle, because you can treat it as if all the charge is centered at the center of the sphere. If the charges are moving, this ain't going to work. Because when charges are moving charges also produce magnetic fields. Okay. Coulomb's law cannot explain a case when a charge experiences an electric force in the absence of other charges. You can have a charge here, Q, and far away, you can have some magnetic field that's changing. And we'll find later this semester that a changing magnetic field produces an electric field. Okay, and we'll talk about what electric field is later. And electric fields exert forces on charged particles. And so that charged particle would experience a force. This equation could not explain that. So there are limitations to Coulomb's law. For the case where the particles are moving, sometimes we do the case where the particles are moving, we're going to assume that the velocity of the particles is sufficiently slow that magnetic effects, other effects, can be ignored. When in reality, it's exactly, it works when, this equation works when the particles are not moving at all. If they're moving, you better hope that they're not moving very fast relative to each other. Okay, so there are a lot of limitations to this, and I'm going to show you another equation that we use to calculate the forces on charges that always works. Okay, so this is very limited, but we're going to start with this equation. Okay, because this is the first equation that was developed in order to study the force on charges. Okay. So what I want to do is I want to compare the electric force and the gravitational force, just to give you an idea of the size of the electric force compared to gravitational force. As we're doing these problems, we're going to be assuming in this unit that charges aren't moving. This is why it's called electrostatics. Well, that's part of it. Also, the sum of the forces in many cases is going to be zero. The sum of the forces on the charge will be zero. Okay, suppose I have two electrons. Okay? The charge on each electron is 1.602. There's more digits after this, but I don't remember them. 1.602 times 10 to the minus 19 coulombs for each one. Their mass, 9.11 times 10 to the minus 31 kilograms. Again, nobody weighed that directly because we don't have scales that sensitive, but we measure them indirectly. What I want to do is calculate the ratio of the gravitational force over the electric force. And if you remember the gravitational force, is given by this equation, G m1 m2 over r12 squared. You did that in Physics 205 a while back. The electric force is K. Notice I have to put absolute values here because charges can be positive or negative. In fact, both of them are negative, so a negative times a negative is a positive. This ratio is going to give me this. So I put in some values, m1 and m2 are equal. And I'm not going to write the units because I'm trying to save space. Okay? I'm sorry about that. .99. All right, this is kilograms. This is Newton, meter squared per kilogram squared. Newton Meter squared per Coulomb squared. So what does that come out to be? And I have the value written. It's about, when I round it off, 10 to the minus 43. That's how much stronger the electric force is compared to the gravitational force. Right? You have to put about 42 zeros in front of the 1. Decimal point, 42 zeros, and then 1. That's how small that ratio is. Okay, so it's a very small force, the gravitational force, compared to electric force. And by the way, the unit of charge, the Coulomb, is a very large force. If you have 1 Coulomb of charge, if you think about it, if you have two 1 Coulomb charges, okay, and you take them and put them 1 meter apart, the force is huge. If you have two 1 Coulomb charges, and this distance is 1 meter, it's 800 billion, I'm sorry, not 800, almost 9 billion newtons. Why don't we experience those forces? I mean, we have a lot of charges in our body. Why don't we experience those forces?
Is it because they're moving?
Not necessarily. I mean, our bodies have more than Avogadro's number of charges. So there is a lot of charge in our body. But why is it that we don't experience those forces? Well, you got to think of the net charge of our body. What do you think is the net charge on our bodies, on average? Are we walking around charged?
No.
No, our net charge is essentially 0. We probably have an equal number of positive and negative charges, and so our net charge is 0. But we have more than Avogadro number of particles. If you take Avogadro's number and multiply by the charge of the electron, I mean, this is going to be hundreds of thousands of coulombs, which is enormous in terms of electric forces. But we have probably an equal number of protons that cancels out that electric force. So overall, our net charge is, on average, is 0. And so the force between me and the person next to me, the electric force, is close to 0. You probably can't measure it. It's very small because the net charge is very small. Okay. But that's a huge force. By the way, I want to show you one more thing about Coulomb constant. The Coulomb constant can be written this way too. Where epsilon naught is 8.85 times 10 to the minus 12 Coulomb squared over Newton meter squared. This is called a permeability of free space. And this Coulomb constant also depends on is the value in a vacuum. So we're going to pretend we're in the vacuum and doing a lot of these problems. Okay, in general, if you're not in a vacuum, you have to multiply K by some number or divide it by some number. Okay, same thing with this one. For materials that have a nice behavior. We'll get to that later. And I'll describe what this means later when we get to chapter 26. But we can write it this way too. Okay, we can write K in terms of 1 over 4 pi epsilon naught, and you'll see a lot of that in books. Just so you get to see it. Okay. Now, we can write Coulomb's law as a vector too. Coulomb's law written as a vector can be written like this. So let me write down two charges. This is Q1, this is Q2. What we're calculating is the force on 1 due to 2. The force on 1 due to 2. And R12 is the unit vector that points from 1 to 2. Okay, R12 is a unit vector. If I was calculating the force on 2 due to 1, then I would have 2 on 1 here. Then I'd have a unit vector that points from 2 to object 1. And whether I calculate the force on this object due to this object, or the force on this object due to this object, how should they be related? Using your knowledge of Physics 205. Using Newton's third law.
They're equal and opposite?
Yeah. Of course, we're assuming that these objects are not too far apart. In reality, Newton's third law, relativity says Newton's third law is really not valid. Okay, but as long as, because you get different, if these particles are far apart, okay, you'll notice that if one of these moves, different reference frames are going to measure a different force between the two objects. Okay, but let's not worry. Let's forget about relativity for now. But where we say Newton's laws are still valid, the forces are going to be equal and opposites. If objects are really far apart, that's not the case. For objects that are close enough together, this is true. Okay? And so this gives you another way. This allows you to write it as a vector. The difference here is you're putting the actual value of Q1 and Q2. When I wrote it before, because people forget this, as a magnitude, I have absolute value signs there on Q1 and Q2 because I wrote F12 as a magnitude. Here I did not. The R12 tells you the sign. This thing will tell you the magnitude and the direction of the force by writing it this way. It's consistent. Okay? We define the vector this way so it's consistent. It gives you the right direction for the overall force if you put in the actual value of the charges into the equation. The only problem I have with this is that it's non-physical. Okay? It becomes, calculating the force on this object due to this guy is just a matter of mathematically finding this guy and just plugging numbers into an equation. So it's non-physical. Do you all remember how to get a unit vector? I know you've talked about it in 205.
The magnitude divided by the vector. Or...
The opposite way, the vector divided by the magnitude.
Okay,
right?
yeah.
Yeah, so R12 unit vector is that. Okay, so I won't spend time on determining unit vectors. This does not give you the direction of the force. If I write it this way, it's not going to give you the direction of the force. This gives it to you right away. This is unphysical, but doing it this way is going to allow me to give me a physical understanding of what's going on. So why is that? I have two charges. I have Q1 and I have Q2. This one's positive. This one's negative. The force between them is given by this equation. What is the direction of the force on this object due to that one?
Wouldn't it be towards?
Towards,
attracted?
right? It's along the line joining them. When I draw that force vector on the charge, what is that picture called?
Is that a free body diagram?
Yes.
Or?
So when we do force problems, guess what we're going to draw first?
Free body diagrams?
Yes, you got to draw a free body diagram. So that's the way I really would like you to do the problems, is by drawing free body diagrams. Okay? That's why I'd rather have you calculate the force this way. Find the magnitude, draw the free body diagram, or actually draw the free body diagram, find the magnitude, and then you can solve for it. You break this vector up into x and y components. As opposed to the other way that I showed you, that you see in the slide there, that's more mathematical and less physical. I'm going to do a problem in a moment where I'm going to do it the physical way. I've created a video, it's in a module, where I do it the other way. And you can take a look at that video. Okay? So you get to see me, you can see the problem done two different ways. Although I do prefer that we're going to do it the way I do it in class, because it's more physical. The other way hides the physics, it's more mathematical. Now, Coulomb's law obeys the principle of superposition because the force acting on a charge is really the vector sum of the forces producing the charge on Q. If I have three charges, it doesn't have to be three. I mean, it could be as many charges as you want to have. If I add this charge here, and I add another charge here, these two are not going to affect the force between these two. However, adding these two charges will affect the total force. And to find the total force, I find the force between these two, plus the force between these two, plus the force between these two. You did that in Physics 205 when you drew your free body diagrams. You just got to add the vectors. That's the law. That's the principle of superposition. You've been using it in Physics 205. That the sum of the forces is just the vector sum of the force vectors. Okay? So whether these two charges are here or not, the force between Q1 and Q2 by themselves stays the same. These don't affect it. However, they do affect the total force acting on Q1. So, how do we solve a problem involving forces on some charge? So the method, I have method 1 and method 2. I'm going to really just talk about method 1. The video that's on Canvas shows you method 2. Okay, and I did that in the interest of time. So, first thing, draw a free body diagram indicating all the forces acting on the test charge. What I mean by the test charge is the charge in question. Okay? Then determine the magnitude and the components of each force on charge Q due to the source charges. Sum the x and y components of the forces to determine the x and y components of the resultant force acting on Q. Take the square root of the sum of the squares of the forces determined in part 3 and determine the magnitude and the resultant vector. And then use the inverse tangent function to find the angle. This should sound familiar because this is what you did in Physics 205. I don't have to find a unit vector. Okay? Doing it this way, I don't have to find really the unit vector. If you do it using the other method where you're just writing the equation for the force vector, you have to learn how to, you have to actually write unit vectors. Okay? Now the other method basically requires you to use this equation you're going to individually calculate this force vector on the object in question due to all the other objects. So you're going to calculate a bunch of these. F12, F13, F14, and then just add up all the vectors. That's really all you do. And that's what I do in the video, but I'm not going to do the problem that way. Even though it's mathematical, the problem is you have to figure these out, which eventually we're going to have to learn how to do for things we're going to be doing a little bit later on. Okay, I don't want to do it now. So I'm going to do this using method 1. I want to calculate the net force on that charge. So let me draw a picture. Okay, and this is an equilateral triangle. In fact, let me draw it. I need space. I guess we'll draw it here. Let me draw the 3 charges. And even though my picture doesn't show it, this is supposed to be an equilateral triangle, okay? Two microcoulombs, bottom left, bottom right, -4 microcoulombs. Top one, 7 microcoulombs. I want to find the force on that top object due to the other 2. So the first thing I'm going to do is draw. And so, I'm going to draw a free body diagram, but let me label things. Let me do it consistently with my notes. Just 1 second. Let me call this object 1, object 2, and object 3. This is a positive charge And this is a positive charge. Let me move the 7.00 because it's going to get in my way. What is the force on this top object due to this one on the bottom left? Are they going to attract or repel?
Well,
So this is F12. Remember, this is an equilateral triangle, so all the angles are 60 degrees. These two have opposite signs. So this is going to, the object 1 is going to be attracted to object 3. If these two charges were equal, what would happen to the y components of the force?
oh, they would cancel.
They would cancel.
So it'd go right, yeah.
Because all the distances are the same, right? That's my free body diagram. And so I'm trying to use another color. Green doesn't work very well. Let me try purple. I'm going to resolve these two forces. Okay, I don't have enough space, but this is 1, 3y, this is 1, 2y, and then this is the x component, and this is the x component. So really, what I need to do is sum the forces in the x direction, and then sum the forces in the y direction. Like I can write it like this in unit vector terms. All right, I can write the sum this way, right?
Yeah.
So the problem is I need to figure out what F12 is. Let's figure out the magnitude of F12.
Wait, wouldn't the F13y be negative?
Yeah, you're right. And I'll put the value in.
Oh, okay. All right.
Yeah, I'm just. You're right about that. I'll put the minus sign in when I put in the value. You see what I mean?
Yeah, no, that makes sense.
Yeah, that's always. We also got to be careful with that with the signs, but. Okay, so F12, 8.99. I'm not going to put the units in because I need space. The magnitude of charge 1. I'm going to do it this way because I don't want to write things over and over again. You see what I did there? Macro is 10 to the minus 6. 10 to the minus 6 times 10 to the minus 6 is 10 to the minus 12. So that comes out to be 0.504 newtons. So the magnitude of F12 is that. F13 And again, when I use Coulomb's law in terms of the magnitude, I put the absolute values of the charges. Okay, so now F1, 2x Does that make sense? And then this comes out to be, uh-oh. I didn't write it down. Just give me a second, because I didn't write down the values. 0.504 times root 3 over 2, and I didn't write down that value. And I don't have a calculator. I'll write it like that for now, okay?
I got 0.430.
0.430?
0.436.
Okay,
Sorry.
thank you.
Yeah.
This is probably not right. Okay. And then we do the same thing for, I ran out
The
of
top
space.
one is right.
Okay. And so let's do the other one. That's not right, sorry. This is where I'll put the minus sign in. So now, 1, 2x is 0.252. 1, 3x is 0.504. 1, 2y, where'd it go? It's 0.436. And when I simplify this, oh, I made a mistake. So now I have the force vector, its magnitude. I use the Pythagorean theorem. It's hard to write down here, sorry. When I add them up, I get 0.873 newtons. And then the angle theta, the inverse tangent of the y component, which is that, over the x component. And that's going to give me 330 degrees, or 30 degrees below the x-axis. So you can say 30 degrees below the x-axis. Another way to write it is 30 degrees south of east. However you want to write it. Okay, so I've done this problem. Even though the nature of the force is different, I've done this problem exactly the way you would do it in Physics 205. And the reason why is because a force is a vector. Vectors is are a mathematical construct. It doesn't matter what the cause of F is. The math is the same. The math doesn't care what the cause of the force is. Okay? If it's a vector, you got to treat it like a vector, and that's what I did. And so I solved this problem using the means of Physics 205, even though the nature of the force is different. Make sense?
Yeah.
Okay. Any questions? And so you have a lot of different problems. So you can, in the homework, and you can do this with as many particles, as many charges as you want. Of course, if you have 100 particles, it's cumbersome. If you have 100 particles, maybe there might be another way to do it. And in fact, if you have a distribution of charges, instead of, these are called discrete charges, right? If you have a point charge and some blob here, how would you do that? Well, you'd have to break up this blob into teeny tiny pieces. You'd have to break this thing up into a bunch of dq's. Find the expression for the force for every dq that makes up this object, and then sum them all up or integrate. Okay, so in order, if you're going to use Coulomb's law, because Coulomb's law is for point charges, you have to actually break this up into a bunch of point charges and add them all up. Of course, if this distance was huge, then you could still treat this like a point particle, because if you're standing here and this blob is really far away, it just looks like a point charge. And to a good approximation, you get the correct result. Okay. So, any questions about Coulomb's law and forces so far? Because now I'm going to talk about something that's related to it, and it's a more abstract concept. It's called the electric field. I'm going to introduce the concept of the electric field, and I'm going to show you how to calculate it for two different cases. For discrete cases and for continuous charge distributions. And of course, discrete cases are always easy to do. It is the continuous charge distributions students have a hard time with. So we're going to do both of them. You have to be able to do both of them. At least using elementary techniques, meaning the techniques based on your knowledge of math so far. These problems can be very difficult. And even when you take this course, if you take this course in graduate school, you actually will study Coulomb's law and electric fields. The only difference is that you're learning mathematical techniques that it will allow you to solve more complicated problems. It's the same principle, just the math is more complicated. Okay. So what is this thing called the electric field? It's analogous to the gravitational field. which you learned about in Physics 205. The electric field gives you an idea of how great a force an object will experience. This object I'm going to call a test charge. And now I want to get an idea of how big a force this thing will experience around some distribution of charges. No matter how, it could be one charge or just a whole mess of charges. Okay, it gives you an idea how big this object, how big of a force this object will feel in the vicinity of this distribution of charges. In fact, I mean, it is like the gravitational field strength, right? Because if you remember from Physics 205, G was the big constant G times the mass of the object divided by the distance between the object and the mass squared. So here's the Earth. And you are standing on it. That force acting on you is downward towards the center of the Earth. The value is 9.80 meters per second squared, right? This is the mass of the Earth. This is the radius of the Earth. Well, it's really the distance from your center of mass to the center of the Earth. But the distance from your center of mass to the surface of the Earth is about meter. This is 6 million meters. That 1 meter doesn't make a difference. We ignore it. Okay. That's the Earth's this is the gravitational field strength. This is the gravitational field, and it's in towards center of the Earth. I'm writing down its direction instead of writing a unit vector, because then I have to define the coordinate system. Okay? And you calculated this by taking the weight of the person, the force, and dividing it by your mass. Right? You took your force divided by your mass and you get G. So I take any object here then, whatever mass I have, all I have to do is take this gravitational field, multiply it by the mass of the object, and I know the force that the object is going to experience. That's what you did in Physics 205. G gives you an idea of how any object, it'll give you an idea of how any object, a force will feel when it's near the Earth. Okay, so that's one way to look at the field. So I'm going to define the electric field as the electric force over the value of the test charge. Why do I call it a test charge? Because I'm going to make it small enough so its effect on the thing producing the field is minimal. So that's how I define the electric field. And for now, the unit is the Newton per Coulomb. I will introduce a new concept later on, and I can rewrite it. I can write this in terms of other units. But for now, we'll write it as a Newton per Coulomb. Okay? This is a Newton per kilogram. This is a Newton per Coulomb. Okay. G in gravity should really represent the gravitational field. I know people call it acceleration due to gravity, but it should be called the gravitational field. That's a more correct term. This is the electric field. So that's the gravitational analog of this expression. For a point charge, it is very easy to write down the expression for the electric field, because if Coulomb's law looks like this, then F12 over Q1, which is equal to E due to 2, that's our electric field. For a point charge, for a point charge, electric field is very easy. So here's charge 2. Here's a location in space. The electric field due to this object here is given by this expression. This is the magnitude. As a vector, you have to put the unit vector in here that's directed from Q2 to that point. So the unit vector goes from the source to the point in question. This is a point in space. There's nothing, it's just a location in space. See, what happens is when you take a point charge and you put it in space, it disturbs the space, because when you put another object in the vicinity of Q2, it's going to experience a force due to Q2. You can think of the electric field as creating, or a gravitational field, as creating a disturbance in space, because when you put that object in space, another object that's placed near it is going to experience a force. And so writing E as a vector I'm going to take the absolute values off. Oops, I messed up. Nobody caught that. Writing E as a vector now. I didn't put a 1, 2 there, and I didn't put a 1, 2 here because there's no charge here yet. Okay, if I put a charge there, this is a location in space. I don't need another object there in order for the field to be there. The field's there because the field's everywhere here because of this guy. When I put this guy here, I can assign a vector everywhere on this board, indicating the magnitude and direction of the field due to this object at that location. All right, I can draw a vector that looks like this, that represents the magnitude and direction of the field at this point due to this guy. I can assign vectors everywhere. It's a unique vector. Again, r hat is a unit vector that points radially outward from the source of the field to the point at which the field is determined. And I'm slowly and carefully saying these terms so that you remember them, because they're important and they cause issues when students are studying this subject. So it's about 12:20. My clocks are all off. By the way, I'm not lecturing from home today. I'm lecturing from campus because I'm having internet issues. I actually have 12:25. So let's take a break. Let's meet at 12:45, and I'll continue this discussion. Okay?
Okay. All right.
All right.
Recording stopped.